Hi, in this video I will summarize the three integral theorems and point out that they can be seen as three different manifestations of the same principle. This unifying principle is also valid in higher dimensions and is called generalized Stokes theorem. I'll present GST at the end of the video, but first let's review the three integral theorems you're already familiar with. The first one is the fundamental theorem of line integrals, saying that the integral of the gradient of a function f over an oriented curve C with starting point P0 and endpoint P1 is equal to fp1 minus fp0. The curve C could be a curve in the plane or a curve in 3 space. Secondly, we have Stokes' theorem, which says the following. If S is an oriented surface in 3 space with boundary curve ds, then the integral of the curl of a vector field f over S is equal to the integral of f over ds, where the orientation of ds matches the one of S in the sense of the right-hand rule. Finally, we have the divergence theorem, which says this. If E is a solid region in 3 space with a boundary surface dE with outward orientation, then the integral of the divergence of a vector field f over E is equal to the integral of f over dE. Now, the expression indicated here is the only expression that doesn't look like an integral. It can, however, be interpreted as an integral, namely as the integral over the boundary of C. The boundary of the curve C is the set shown here. It consists of the 2 points P0 and P1, having negative and positive orientation respectively. Okay, so each of the three theorems expresses an equality of 2 integrals. Now let's see what these 3 equalities have in common. In each of them we have, on the left-hand side, an integral of some kind of derivative of a function or a vector field over some object, and on the right-hand side, the integral of that function or vector field itself over the boundary of that object. So, loosely speaking, each of the 3 equalities has the format shown here. To make this more precise, we need to look at integrals as integrals of differential forms. Before I go into this, let me first simplify the notation of the 3 theorems by using a single integration symbol for each of the 6 integrals. Okay, now let's have a close look at the first equation. On the right-hand side, we have a function under the integration symbol. On the left, we have the expression shown here, which is a differential form of order 1, also called a 1 form. In the language of differential forms, the function on the right is called a 0 form. Note that the 0 form does not contain a differential at all. It's just a function. Now, the 1 form on the left is actually equal to the differential of the 0 form on the right. So the first integral theorem can be written in the succinct form shown here. On the right-hand side, we have the integral of the 0 form f over the 0-dimensional object dc, and on the left, we have the integral of the 1 form df over the 1-dimensional object c. Now we're getting somewhere. It turns out that the other 2 integral theorems have a similar structure. Let's re-examine the second theorem shown here. On the right-hand side, we have, under the integration symbol, the 1 form shown here. On the left, we have the expression shown here, which is a differential form of order 2, also called a 2 form. The 3 expressions indicated here are called wedge products. The basic rules for such products are shown here. It turns out that the 2 form on the left is actually equal to the so-called exterior derivative of the 1 form on the right. The exterior derivative of a differential form of higher order is a generalization of the differential of a function. I won't go into the general definition here. The upshot is that the second integral theorem can be written in the succinct form shown here. Hence, we have an integral of a one form over a one-dimensional object on the right, and an integral of a two form over a two-dimensional object on the left. Finally, let's re-examine the third theorem, which has a two form under the integration symbol on the right. On the left, the expression under the integration symbol is the three form shown here, which turns out to be the exterior derivative of the two form on the right. Hence, in the third theorem, we have an integral of a two form over a two-dimensional object on the right, and an integral of a three form over a three-dimensional object on the left. So each of the three integral theorems has the format shown here, where omega is a k-1 form and d omega, the exterior derivative of omega, is a k form, while m is an object of dimension k, and dm, the boundary of m, is an object of dimension k-1. So here we have it, a clear formula which unifies the three integral theorems. Now the great thing is that this formula does not only hold for k equal to 1, 2 and 3, but for all k greater than or equal to 1. In this more general setting, the formula is referred to as generalized Stokes' theorem. What can we say about m in a general setting? What kind of object should it be? Which properties should it have? The three objects C, S and E are 1, 2 and 3-dimensional objects contained in R2 or R3. These objects are special cases of what in general is called a k-dimensional manifold in Rn. I won't go into the general definition of a manifold here. Okay, so C, S and E are manifolds. More specifically, they are closed, bounded, smooth and oriented manifolds with a boundary with induced orientation. We have now reached a point where we can state generalized Stokes' theorem. Here it is. The integral of d omega over m is equal to the integral of omega over dm, where m, dm, omega and d omega satisfy the specifications shown here. As you can see, there's quite a bit of math contained in this theorem that is not covered in the first-year calculus course. For those of you who would like to do some further reading, here are some references I could recommend. That's it for now. I hope you've enjoyed watching this video.